everybody. Welcome to this session. Okay, I will wait just 1 second for you to wear your headset. Okay, so I hope you hear me well. Today I'm really excited to introduce these sessions, mainly because we have a great startup that we have the honor to work with. But first of all, as unfortunately many of you already know, cancer affects millions of lives. Today we have the chance to appreciate the incredible work that Sonrai Analytics did when it comes to drug development and cancer treatment development using AWS services. So before we dive in, let me introduce the team that will guide you today through this journey. So I'm Camillo Anania. I'm a principal solutions architect at AWS. I'm joined by my colleague Onat Selman, which is a senior solutions architect. And we work every day with startups like Sonrai Analytics. We are really excited to have Gerard Loughran, head of engineering at Sonrai Analytics, that will explain the incredible journey they had with us so far. First of all, let's go briefly through the agenda to see how this is relevant for you today, this session. I will start the first two sections. First of all, I will cover the healthcare industry challenges. Many of those, for who is familiar and working in the sector, will resonate with you, I expect. And afterwards, we will explore a little bit what AWS has to offer to address those challenges and those roadblocks. After me, we will have Gerard that will go through the Sonrai Analytics journey with AWS. And finally, we will have an architectural deep dive with Onat, where you can appreciate also the details, the technical details behind the solutions that we are going to speak through this session. So first of all, let's start with the challenges in precision medicine and why you should care. The first one is around workflow complexity. If you work in the space, I'm sure you're familiar. You have a team of biologists, data engineers. They have to work together to bring to life those genomics pipeline and to process terabytes of data. So those workflows need to scale, needs to be efficient, needs to work well. So this collaboration is not trivial. It's usually, there is usually conflict and friction, and this basically translates in costs. Afterwards, of course, this is a highly regulated industry. You will have a lot of requirements around compliancy, security, auditing, tracing, and so on. Privacy, making sure your data are region locked and you can demonstrate that your data didn't move from a specific region, for example. And one more that is also very important is medical data, of course, are of different types. You have genomics data, you have lab results, you have imagings, medical imagings, and so on. So it's about also to process all those data and to break the silos so that you can get better insights from those data. So keeping those challenges in mind, I would like to introduce you to a service we introduced a few years back, which is purpose-built to address those ones, which is called the AWS Healthomics. So picture the scenario where your team gets terabytes of data that needs to be processed. So typically what happens is you go through weeks of processing time, you have multiple teams coordinating, you need to handle the infrastructure that needs to scale to address and to tackle those processing. So let's see exactly how this service can help tackle these challenges. First of all, it simplifies the workflows, but how? So it provides ready-to-run genomics pipelines. For example, NF core, the set of NF core that are very common. so that you don't need to recreate those or customize. They are just ready to run, and the most common one in the industry are available. After all, you can also create your own. It supports the most common workflow language like Nextflow, WDL, CWL, and so on. But most importantly, and this is, I think, is the most important value of this service, it provides real impact because it can scale very quickly without any manual intervention, so automatically, to address thousands of processing in parallel. So when it comes to security and compliance, it comes with built-in security controls. It's HIPAA eligible. It has all the controls you might need to be GDPR compliant. You have full audit, trails, logs. For example, if you need to do an FDA submissions, you will have to provide those data. And this service out of the box will provide you with this information. And finally, when it comes to data silos, this is a service you can use to do multi-omics and multimodal analysis out of the box. Not only that, it supports, it integrates with AWS analytical service, so you have full flexibility. I mean, AWS provides a vast array of analytical service, very powerful. So you have basically unlimited capability when it comes to, customize the type of analytic that you want to do on those data. So now let me move on to the next set of challenges that we are going to explore a little bit better with Gerard and Onat, especially when it comes to the real world use cases, right? How this is done. But when it comes to the challenge about AI imaging, first of all, we need to mention data storage. Some of you might be aware, just a single scan is 50 gigabytes of data uncompressed. So if you need to scale this to millions of patients, this becomes a huge amount of data. And it's not just the cost that anyway can be quite high and can eat in your budget if you need to implement one of those type of workflows. It's also the speed of analysis, because you have all this data and you need to access them quickly, because the analysis and the diagnosis can't wait, can't be stopped by and slowed down by a technical bottleneck. The second one, of course, is about AI/ML. You have a foundational model that needs to analyze this image and needs to provide the diagnosis. And here the cost again is critical, because first thing, you need the ability to scale, and second thing, you need the ability to just spend for what you use and add a weight to the performance that you get. And final point, if you implement such type of solutions and you get, for example, a new customer, a new big customer, you need to scale very quickly. And this service enables you immediately and automatically to address all your scaling needs. Okay, this slide, I appreciate this slide is a bit too busy. Bear with me. We will have a chance to unpack it in a bit more details in the next two sections. I just want to provide you a little framework to understand what AWS provides when it comes to AI/ML. So there are different layers to address different needs. So starting from the top, we have specialized and core services. These are basically AI services that you can access with an API. For example, you have Textract to extract text from images, speech to text, and so on. So you just use an API, and you don't need to recreate the model that is behind those AI/ML capabilities. When it comes to healthcare in particular, AWS provides specialized services. We covered just now Healthomics, of course, but we have a few others. We have HealthScribe to transcribe medical notes. We have HealthLake to store electronic health information, and so on. Finally, and what we are going to see later on with Sonrai Analytics, we have an end-to-end platform we call SageMaker. So SageMaker is a platform that provides all the features you need, from training the model, preparing the data, do the inference, monitor when the model is in production. So basically end-to-end to do AI/ML, addressing all the challenges we just mentioned earlier on. So it will store all your data in a very effective way. It is a managed service that takes care of deploying the model, scaling it, giving you an endpoint that you can use, and makes your life easier. Having said this, let's go into the details and into the exciting part. I will pass the presentation now to Gerald from Sonrai Analytics. Thank you.
Thank you, Camillo. Hi, everyone. I'm Gerald Loughran. I lead the engineering team at Sonrai, and we are an AI precision medicine startup that was founded in 2018. Sonrai uses AI and machine learning to help biotech and pharma companies to make faster, safer, and more accurate decisions. We provide an AI-powered workbench that helps them manage, process, and analyze all of that complicated multimodal data that Camillo mentioned. Today, I want to talk about 3 big ways that we can use AI to support precision medicine: discovering new drugs and cancer treatments, identifying biomarkers to help apply the right treatment to the right patient, and also developing patient diagnostics, like early detection cancer algorithms. We work with AWS to deliver real-world impact and ultimately to help biopharma companies save lives. 1 in 2 people will get cancer. 10 years ago, I would have said 1 in 3 people. And the problem is not only that cancer is becoming more prevalent, it's also becoming a bigger healthcare and research challenge. Camillo mentioned this growing complexity, the need for multiple modalities like RNA, DNA, clinical data, imaging data, and it's really difficult for biotech and pharma to keep up with this. In addition, we all probably know clinical trials are notoriously expensive. They're very time-consuming. They can take years or decades to complete, and they have a very high failure rate, 90%. But AI can help streamline this process and allow us to make more affordable and accessible development for biopharma. In many ways, I would argue we need cloud and AI just to meet these data demands, just to meet the scale. And that is the big blocker stopping us from discovering that next big cancer breakthrough or that treatment. Having that technology that can handle the data complexity, handle the big data volume, and enable biotech to do the experiments that they need. But as Camillo mentioned, there are also some other big challenges unique to this space. You have a need for strict data governance and clinical trial compliance. You also need what we refer to as a trusted research environment. This is a place where you can bring all of your data together, all of your users, all of your tools, run all experiments, have everything audited and tracked and traced so that you can show a full lineage of how you came to your finding. Camillo also mentioned the problem of breaking down data silos. This is a particularly big problem for healthcare, where it's a very fragmented market. We work with companies that might use 20 different tools to analyze 20 different types of data, and they might even store them in 20 different locations. And yet, we need to align and harmonize and centralize that data to make those big discoveries. Reproducibility is also critical to succeed in a clinical trial. You must know the full history of everyone who worked on that data, how you came to your finding, how you validated it. It's a very strict standard. And lastly, of course, it must be technologically scalable. It needs to handle big data, needs to support multiple modalities, needs to have massive compute workload capabilities, and it needs to be affordable. Otherwise, biopharma won't use it. And we all want biopharma to be using AI in the latest tools, because that's how we fight cancer, that's how we make progress. So we've covered the challenges and the requirements. Let's talk about how we use AWS. We provide each customer their own private cloud using AWS orgs. This is a single tenant, fully segregated, compliant sandbox where biotech and pharma companies can discover, develop, and deploy their R&D or their clinical solutions. And that end-to-end flow is really critical for that clinical trial compliance. The discovery phase is about building that trusted research environment, bringing all that data into one place. We also use a data mesh architecture so that we can have all those modalities centralized and harmonized. And then we perform advanced multimodal data analytics to discover the value. We use services like AWS Healthomics, Athena, RDS, Glue. And discovery is also where we can, for example, tell a pharma company, this is the biomarker with the best return on investment. This is the best drug target response rate. We then make it easier for these companies to develop their own algorithms, data products, or cancer diagnostics. They can use code or no code. They can use services like SageMaker, Studio, Notebooks, Lambda, Fargate. And lastly, we deploy all of this using AWS CDK, the Cloud Development Kit. This is an infrastructure as code solution. It's how we can guarantee a consistent, safe, secure, reproducible environment that's been pre-configured for best practice MLOps, security, role-based access control, protecting patient data, all the critical things that you must have to run safe experiments. In front of this AWS architecture then is our multimodal data discovery platform, which we call Sonrai Discovery. This directly addresses the key challenges which Camilla has mentioned. It helps us enforce data governance and protect the data and scale it up. It allows us to run complex biological pipelines, such as through Healthomics. We handle multimodal analytics, including imaging data. And also, you can build your own applications, algorithms, and software, all within the same environment. And then lastly, we capture those insights, we aggregate all of that data, and we help them make better informed decisions, such as which drugs should they take to market, which clinical trial process should they go through. The key thing is all your data, all your tools, and all your users in one place. Everything under one roof, where data can be combined and experimented on safely, rapidly, and cost-effectively. Today's session is going to focus on two key services, how we use them, why they're so important. Camilo's done a great job explaining how Healthomics works, how you use it to process biological data like RNA, DNA, protein. I'm going to give some real-world examples about how challenging that is and just how effective. We're also going to look at Amazon SageMaker. We can use this to train and deploy algorithms. We also run AI foundation models to further streamline development. But SageMaker is also our end-to-end tool. We do everything from train and develop to run processing to running inference. Pharma and biotech tend to favor peer-reviewed or recommended pipelines that are hyper-specialized for each data or omic type. So for example, RNA-seq is used for RNA sequencing data, Quantum-S for protein data, and there's genomic pipelines, there are imaging pipelines, and they all have extreme scientific nuance to handle each individual data or omic type. Sonrai works to modify and integrate these so that we can create those combined data sets and to break down those data silos. But bioinformatic pipelines are really difficult to get right. There's a very high bar to entry and lots of things can go wrong. We've spoken to many companies that have tried and failed to do this themselves, and they have faced sky-high costs, they've risked data breaches, or they've just completely screwed up their data. And to give you a technical concept of the scale, a single pipeline experiment processing, say, 100 patient samples might spin up 10,000 ECS tasks with maybe 80 unique Docker containers running the logic. And this could run for 6 or 7 days. So these are very large, computationally intensive tasks. And we make them as simple as filling out a form and clicking start. Adding to the complexity and the clinical trial challenge, the need for processing this type of data is becoming increasingly mandatory to successfully pass a clinical trial. So Sonrai looked at many different solutions before we eventually chose to build into Healthomics. We had looked at EC2 server Nextflow options, we had looked at AWS batch jobs, and we looked at other external providers. but there are a lot of benefits out of the box with Healthomics. As the name implies, it's built with healthcare governance in mind. It's got great built-in observability, and it generally helps simplify an otherwise very complex and error-prone process. The most obvious benefit here is obviously the cost reduction. Some of you might not even be able to see that there is 2 tiny green lines there, such as the ridiculous difference in cost. And to add some context to this, because the barrier to entry is so high, because biotech and pharma might not have data engineers, cloud engineers, biologists, bioinformaticians, they'll often outsource this work to labs or service providers. And one of our customers was quoted almost $70,000 to do a run that we ultimately did for less than $1,100. And we have clients that do hundreds of pipelines a year, and they might otherwise be paying millions in outsourced fees. That difference, by the way, also worked out $105 per patient sample versus just 1.6. So again, dramatically scaling up the ability to perform this type of research. It's critical that these companies do use these tools, that they do run experiments. So they need to be affordable, they need to be accessible, they need to be easy to use, because this might very well be how we discover those next game-changing drugs. Okay. So switching track, we've talked about how we can use AI to discover drugs and key biomarkers. Let's show you how we can diagnose cancer. And to give you some initial patient context, whenever you're suspected of having cancer, you'll quite often be taken to get a biopsy or a resection. You'll undergo an invasive procedure. Some tissue could be extracted from your lung or colon, for example. That will then be taken to a lab. It'll be placed in a glass slide. A pathologist will then take a marker or a pen and quite literally draw around the area, the region of interest where they suspect you might have a tumor. That will then be scraped off of a sample and processed through various lab equipment. If the patient is lucky, they'll hear back within a couple of weeks. So this is a very slow and expensive and unscalable process. Computational pathology is the process of digitizing that instead. So we take that glass slide and we turn it into a whole slide image, such as that top sample. So you can view it on your computer, you can digitally zoom in like a microscope, a pathologist can draw a digital annotation remotely at home, and of course, we can run AI analysis over that data. It's also worth mentioning that these images are massive, so they need to be layered according to the zoom level, and they need to be tiled or broken up into chunks just to make them work reliably on a system. AI can help pathologists make this process more scalable and potentially save millions in operational costs. And let's walk through the process then of how do we design an algorithm right through to release. Unsurprisingly, there's a lot of processing and data preparation required, and I would argue that this almost necessitates cloud and AI just to manage the scale. 2,000 patient slides, for example, may not sound like a lot, but it's actually 1.2 billion tiles which must be stored, annotated, and analyzed. And many companies simply can't handle the scope or the scale or the cost of that. And of course, there's a critical need to do this in a trusted research environment, to prove you built your model correctly, to iterate, to review, to track your performance metrics, think about sensitivity, think about patient safety. There's a very high compliance requirement. Sonrai uses AWS so that we can build automated ETL imaging pipelines that process this data for us. And then we use SageMaker to run foundation models, which can then dramatically cut down the development time of the analysis. Ultimately, it makes it more accessible and more affordable to biopharma. Sonrai used to use on-premise servers, but now we've moved fully to the cloud. So we do all of our algorithm training on the cloud. And data ingestion is really easy. A pathology lab can just send data to an S3 bucket. Could be an SFTP, so you just drag a file across. Could be a bog standard data uploader. When that data lands in the bucket, which is usually a 5 to 12 gigabyte TIFF file, that will trigger the automated ETL pipeline. That pipeline was written in Rust and uses serverless event-driven architecture, and Onit will shortly walk us through all of that. And it can spin up thousands of these at a time. We can process all of our imaging data, and it's really fast, cost-effective, and reliable. And its job is to make this data AI ready. And once we have that, of course, our tool of choice is then SageMaker to start training and tuning models, to start iterating, to start evaluating. And because it's the cloud, we can spin up as many GPUs as we need to handle any operational demand. The key business requirements for running these algorithms is also to ensure that it's an automated process, it's serverless, it's event-driven. Particularly in clinical and pharma standards where you have to think about maintenance, you have to think about legalities and compliance, having low maintenance, vulnerability-free software is really important. It's also tied to patient safety. So we can spin this up and run thousands of operations without having a heavy maintenance cost for the clients. We've personally tested this on 40,000 simultaneous instances, where we've taken all those slides, we spun up a task for each, they last a couple of minutes each, and then they return the results to the platform where a pathologist, for example, can make a decision. It's also a very flexible environment, which unfortunately is required because cancer is not one size fits all. Neither are the disease types. These companies must be able to swap out their foundation models, swap out Docker containers. They need to have custom logic and preparation to handle each disease type that they focus on. So looking under the hood of our tumor detection algorithm and how we use foundation models, we take the whole slide image, we break it up into tiles, which might be, say, 600,000 tiles per image. We then use a foundation model to run feature extraction. And what we end up with then is clustered or grouped data. So for example, the algorithm has picked out all the tumor tissue, all the inflammation, all the stroma. We can also generate embeddings, which can then fit into a multimodal data infrastructure, meaning you can now analyze imaging and tabular data side by side, unlocking new experiments and opportunities, and also dramatically reducing storage costs. Within the last year, we've also started working with foundation models, both public and private, and they have been trained on millions of these whole slide gigapixel images. And this provides a really rich base for advanced AI and machine learning. It dramatically streamlines the development process, it reduces the barrier to entry and the cost, and just the general technical difficulty. And this is what it looks like in practice. So this is a patient's whole slide image, and an AI algorithm has generated that result. The area in green is tumor tissue that's been pulled out, and you can also see some other clusterings that we've identified, like artifact and information. This was an entirely automated process. The lab sent the patient sample to the S3 bucket. That triggered the ETL processing. That then triggered the analysis inference. And then we end up with a digestible, explainable result where a pathologist or clinician can potentially make a decision with a patient. And it also, again, supports multimodal data integration, which means this can be combined with RNA, DNA, health omic-based data to do more advanced research. We provide this to biopharma companies so that they can build their own cancer detection algorithms, their own disease diagnostics, their own solutions that can help patients. It reduces complexity, increases accessibility, saves time and money, so the companies are willing to invest in this in order to develop those new breakthroughs. Unsurprisingly, training an AI imaging model is a pretty intensive process. And I mentioned that we previously used on-premise servers. We had a really great one. We had fantastic NVIDIA GPU cards. We used tools like Slurm to handle parallel processing. But thousands of tiles and billions of tiles and thousands of images were just too much for that workload. So when we roughly had about 100 days still to go for our own model development, we built our cloud tile extractor, written in Rust using Lambdas, and it was able to complete that remaining work in just 6 hours, which, first of all, made us stupid that we left so long to try it, but secondly, allowed us to move our product forward 6 months. It also is what our customers now get out of the box. They can streamline their preparation, they can reduce the time it takes to build an algorithm, and they can potentially get to market 6 to 12 months faster. Another interesting challenge is actually just showing that image on a screen. It's trying to manage the cost, the scale, the usability. One of those images alone is 5 gigabyte in a compressed format. But when you extract it, it's more like 50 gigabyte because there's 600,000 tiles inside. And we have companies that have petabytes of these whole slide images, and their storage costs were crippling their operations. We've spoken to companies that are spending millions just to host their imaging data. But Sonrai's cloud-native image viewer instead spins up thousands of lambdas at a time, reaches into that single SVS archive, and just lazy loads the tile as we need it. It does this in real time, it loads in milliseconds, essentially rendering the equivalent of 50 gigabyte. So again, it's also really cost effective, and it reduces the overall storage cost by a factor of 10, because you're no longer storing all the tiles, you're just using the base image. It also critically avoided the need for data compression, which in a clinical trial, or if you're developing a sensitive algorithm, that can be a deal breaker, that can get you shut down by the FDA. So lastly, to summarize the real world impact, Camillo and I have hopefully did a good job explaining to you the problems with data complexity, and also that AI and cloud are maybe the most obvious ways to help alleviate this so that we can scale those breakthroughs. Sonrai's technology is used today by biotech and pharma companies to help them build their own solutions, discover new drugs, get cancer diagnostics out. But Sonrai's own algorithms can also do in 3 minutes what takes a lab 2 weeks. And again, it's almost infinitely scalable. AI can help discover new drugs and treatments. It can make it more affordable, more accessible, ultimately scalable. And the end result is better outcomes for patients. I'm now going to pass you over to Onit, who's going to walk through the actual serverless architecture and how we do it. Thank you.
Thank you, Jared. As we just heard, the healthcare industry faces significant challenges, from maintaining compliance and governance to ensuring robust security, managing complex workflows, and breaking data silos. Camillo effectively illustrated these pain points. Jared then demonstrated how Sonrai tackles these challenges head-on using AWS services, with AWS Healthomics at the core of their solution. This presentation focuses on 2 key architectures: AWS Healthomics implementation and imaging inference architecture. This architecture implements complex workflows while meeting with healthcare industry requirements, providing high scalability, high availability, and cost efficiency. The presentation will break the architecture in 3 key components, each highlighting specific data flows and AWS services to illustrate how Sonrai utilizes AWS Healthomics to transform healthcare data management through an innovative end-to-end multi-omics solution. In this architecture, authenticated users with least privileged IAM roles upload genomic and omics data, including FASTQ files, to an S3 reference bucket, which feeds into AWS Healthomics private pipeline. Sonrai Analytics runs multiple pipeline workflows, managing up to 10,000 concurrent computations for week-long computations at petabyte scale. And they process different omics data types, including DNA, RNA, and protein. AWS Healthomics ensures regional compliance by controlling where data is processed and stored, providing comprehensive audit logs. This is crucial for clinical trials and FDA approvals. Results are stored in a separate AWS Amazon S3 bucket that enables bidirectional data flow between AWS Healthomics for future pipeline executions. The new pathway integrates AWS SDK with AWS Lambda functions with specific IAM role to publish filtered data. Lambda processes data from the primary AWS Healthomics workflows and optimizes storage through filtering by object data type and size, and stores refined results in a dedicated S3 bucket. We can call this refined results S3 bucket. The architecture implements two distinct IAM roles, one for AWS Lambda invocation, another for AWS Healthomics pipeline invocation. Adhering to the AWS's best practices, the principle of least privilege for security and compliance. The use of Lambda and this serverless approach offers advantages, including event-driven processing, auto-provisioning and scaling, and cost optimization through pay-as-you-go pricing model, and seamless AWS service integration while maintaining strict security controls. The architecture enables data analysis through multiple pathways. Amazon Athena for serverless analytics, Amazon SageMaker Studio for deeper analysis, and custom code through notebooks using S3 as a data lake. For genomics research, particularly single-cell RNA sequencing, Amazon Bedrock's large language models integrate effectively through SageMaker Studio. Earlier, Camilo highlighted the persistent challenge of data silos in healthcare industry. Athena addresses these data silo challenges in life sciences by enabling seamless analysis of diverse data types and pipeline results using SQL, all without infrastructure management. The analysis results are stored back in and presented back to the user using Sonrai's Insights platform through visualization. Now, I'm excited to walk you through Sonrai's next solution, the imaging inference architecture. This is where things get really interesting in terms of processing medical imaging data at scale. It's an event-driven, serverless solution orchestrated by AWS step functions that leverages Amazon SageMaker AI for inference. To help you grasp the full scope of the solution, I'll break it down into two key components, each highlighting specific flows and AWS services. The Sonrai Discovery Applications front-end architecture leverages multiple AWS services. Amazon RAS 53 provides DNS resolution, while AWS WAF and Amazon CloudFront with AWS Shield provides Layer 7 and Layer 3 and 4 DDoS protection respectively. User authentication is handled by Amazon Cognito, which issues temporary security credentials through IAM roles. The Angular-based application is hosted on Amazon S3 as a static website, distributed globally through CloudFront. When authenticated users interact with the interface, The AWS SDK triggers step functions workflows, creating a scalable serverless architecture for inference, imaging inference orchestration. Let's zoom into AWS step functions workflow. Our serverless AI pipelines with a Lambda function fetching customer-specific algorithm version from parameter store. Managed through a pull request initiated by the customer for compliance, auditability, and repeatability. The Lambda publishes to SQS, enabling a decoupled architecture, after which SageMaker AI fetches algorithms Docker image from Amazon ECR for further inference processing. Earlier, Jared shared the scale of data, total storage reaching to petabyte scale. The pipeline handles large medical images between 5 to 12 gigabytes compressed, 50 gigabytes uncompressed, all stored in S3. Post-inference, another Lambda function stores the result in Amazon RDS via AWS AppSync, chosen for its real-time updates and seamless data synchronization capabilities across multiple data sources. Let me recap our architecture. Each customer has a dedicated AWS account for security isolation, where step functions orchestrate serverless event-driven workflows. The integration with SageMaker AI creates a comprehensive imaging ETL pipeline that achieves 3 core benefits: high scalability, 40,000 plus concurrent workflows, cost efficiency through pay-as-you-go pricing, and flexibility in utilizing multiple foundational models. And with that, we have come to the end of our session. Please take a moment to complete the session survey. You can do this easily through the Summit app or by scanning the QR code displayed here. We will be around here and at the AWS Startup Loft area for continued conversations. And you can also find all of us on LinkedIn. Please don't hesitate to contact Sonrai and Jared for follow-up conversations as well. Thank you all for your attention today, and I hope you enjoy the rest of AWS Summit London. Thank you.